Okay, so this is, me, Cliff Click, trying to get conversations going about compiler-related things, language implementations, and runtimes. I don't have any other agenda. The conversation goes where it goes. I run an open mic policy. I reserve the right to moderate if people get, excited. Hasn't been necessary. Other than that, I ask that you keep yourself muted if you're not talking, mostly because we get 10, 15, 20 people. Today, they're like 15 people said they're going to show. There are 7. Tomorrow, 20 people claimed on Twitter voting that they were all going to show. We shall see who actually shows. But the usual thing is between 15 and 20 people. So 15 mics open leads to all kinds of background noise. That's not tolerable. After that, after Dennis is done, I think we just Q&A, however you want to do it. We just go round table. There's no one's in charge other than I'm trying to make the conversation flow. And with that, I guess I'll hand it off to Dennis, who has slides that I attempted to send to people, but I think that was the failure for the email to go, is that Google didn't like me sending out 50 copies of slides. So put them up, screen share them. Dennis, I'm going to make you screen shareable if I can figure out how to do it.
Okay. I have a share screen button. Should I?
Yeah.
Right. Okay. Oh, okay. Host disabled. Yeah. So
yeah. Okay.
You should probably give me the ball.
Yep. I attempted to just now give it to you. See if you can do it now.
Okay. Oh, right. Here we go. Can you see it now?
I can see it.
All right, good. So, okay, let's start, right? So, thanks, Cliff. I'm glad to be here. Thanks for having me. Today, we'll talk about performance monitoring counters. So, I work at Intel. I'm a C++ compiler developer. We are doing pretty much heavy optimizations for CPU, for CPU servers, and yeah. So it usually involves like a fair amount of flow level performance analysis, including capturing and analyzing performance monitoring counters. So let's start. What is performance monitoring counters? Well, okay, let me click. All right. So if you just finished the computer architecture course, this will be the CPU mental model of how the CPU works, right? So we have a pipeline like let's imagine that it's a classic five-stage pipeline. We have caches, we have branch predictor, and then we have a clock that send pulses and makes everything everything goes to the next stage. All right. Now, if we just add a little bit of silicon, we can build a new hardware register, and if we connect it to clock generator, then we can actually count cycles. Well, I mean, count cycles is not too impressive, right? So if we connect our new counter to the caches, to the branch predictor, and to the execution pipeline, then suddenly we can count actually more, and we can count different events. We can snoop into caches and count cache misses. We can snoop into branch predictor and count branch miss predictions, and we can snoop into the execution pipeline and count instructions retired and so on. Notice that we also now have the configuration register, because now we need a way to tell what exactly we want to count, right? So, and then if we want to count multiple events simultaneously, then we actually want to have multiple performance counters, and we have the control registers for them. And then there is a global control register, which can disable and enable all of them at once, or just disable or enable some of them, so sort of have global control. So architects actually try to lay out all those counters in such a way that at least that every unit will be connected to at least one of the execution counters, in order so that you know, so that multiple events from the same unit can be counted simultaneously. Okay, if that makes sense. But yeah. So actually, a little bit of a background. So I think the performance counters were first introduced in the alpha chips. It was probably around late 90s. Then they appeared in Pentium processors. Yeah, and initially they were designed as a debugging feature, not as a way to do performance analysis. So, but later people figured out that, well, okay, we can use performance counters for also measuring performance and have different insights. All right. So inside modern CPUs, well, I will be talking about Intel CPUs today, but to a large degree, all those concepts also actually apply to, for example, to AMD CPUs and yeah. So inside the modern CPUs, there is a performance monitoring unit, or PMU. So it consists of multiple hardware features, like performance monitoring counters themselves. There is the last branch record and other stuff that actually we will not talk about today. But we will talk about today the performance monitoring counters. And then there are performance events that can be measured, right? So every unit has its own set of performance events that can be measured or are countable. Yeah, so and actually, so performance monitoring unit also usually evolves with every new hardware generation. So how you can query your PMU and see what's inside. So typically, performance monitoring unit has three fixed counters. They usually count instruction retired, reference and clocks and reference cycles and CPU cycles. Those are different. And then there are 4 programmable counters. It means that three counters are fixed always, but 4 are programmable. You can measure whatever events, whatever performance events you want with those 4. Okay, they are 48 bits each, and they are implemented as a model-specific registers. What that means? It means that they it actually, so you cannot rely on them being present in particular hardware generation. So they are model specific. They change from CPU generation to generation. You should always first query if you want to do a low level sort of measuring yourself, which you probably shouldn't do, but if you want it, you should first query using CPU ID. Right, so those counters are accessible via read MSR and write MSR instructions. Those instructions are ring 0, so it means that only you can only invoke them from the privileged code, right? Right. Okay.
Yeah, Dennis, you can assume that we're all reasonably expert programmers, certainly in language design and implementation of various kinds. Fair number of people here do compiler code generation for a living.
Sure. Okay, got it. Yeah, sure. Yeah, like feel free to interrupt me, whatever questions you might have, or
suggesting you roll along a little faster.
Okay, got it. Yeah. So this is actually another way of querying your PMU. Nothing too fancy here. Let's just move on. Before actually going on, I want to briefly talk about, well, performance counters, right? But what can we do with them? So there are actually two main methods for using counters. The first is counting events. The second we will talk about in the next slide, but well, okay, counting events. So this is the simple one. What you do is you set the counter, you essentially reset the counter to 0. Then you configure the event that you want to measure. You enable the counting and you let the benchmark go. When the benchmark stops, you just disable the counting and read the value for this counter, right? So this is the simple use case. You're just measuring particular performance event. And this is actually essentially what perf stat is doing. So this is used for workload characterization, for example, TMA, which stands for top-down microarchitecture analysis, which I actually also have a slide for this. So, okay, so the second concept is sampling. So I'm sure you're familiar with sampling. Some people call it profiling, but well, I believe that the more technical term is sampling. In sampling, what you are doing, you're set the counter to count, for example, some event, well, let's say cycles, and initialize it with some number n. I will talk later about what this n means. Then you enable the counting and you wait until the counter overflow, right? You remember, this counter is counting events, so it will be incremented. If you count cycles, it will be incremented every cycle, right? So, and eventually it will overflow. So we start the benchmark. We let the benchmark go. Well, okay, but eventually the counter overflowed. We get the interrupt. This is called the PMI, the performance monitor interrupt. So the hardware raises.
Can you read other performance registers at the same time with the interrupt? Like what's the overhead of the interrupt, and can I read all the other performance counters?
What's the interrupt? So when you read the other performance counters?
Yeah, you say you have 4 that you could sample, three guaranteed, 4 you could program.
So the performance counter you can read on user level. So any level you can read them. The only ones and you can only set them at the kernel level.
Gotcha.
But yeah, the interrupt will take about like 2,000 cycles to 1,000 to 2,000 level to reach the point. That's why the interrupt normally you cannot go to too much high sampling frequency. Otherwise, you measure yourself.
Gotcha. Thank you.
Right, and then actually, so the next thing is, well, you know, you're actually usually sampling on only one event. So that means that you are mostly caring about only this event. You know, you can also sample on multiple events.
Assume what I care about and what I don't. I've happily used a lot more than one at any given point. It's fine. Let's just roll on here. This is like, well, why am I sampling at all? What am I doing here? Well, I'll probably care for a whole lot of things when I sample. That's fine. You just got as long as the overhead's, you know.
You probably care about the whole lot of things when you count events. When you sample, you probably want to know, like.
Oh no. I know the difference between counting and sampling, and when I sample, I care about a lot of things. It's fine. Let's roll on. Let's save that for discussion. If you want to go there, let's save it for discussion. Right now, let's just roll through the slides here.
Sure. Yeah. Okay. I actually don't have much slides left, but we can have a discussion right now or whatever fits. Yeah.
All right. Can you hear me? All right. One question. Can I ask something? Or?
Sure. Yeah.
So what are the implications here of doing this on a live system where I'm not characterizing, but I'm trying to optimize by taking feedback from the performance counters and doing some kind of you know, parameter setting of my virtual machine, or I'm trying to configure my software stack on a live machine by taking feedback from the PMU. In terms of overheads, is it advisable, or is it people doing that? Or?
I heard 2,000 clocks for an interrupt.
But to read the counter, actually, it's only take about 20 cycles. So read
Okay,
counter,
what's
you
the
can do
interrupt doing
reasonable.
then?
Interrupt is basically the kernel try to abstract this counter for you. So you don't need to, like, for example, you want to measure the instructions for the process A, and the process A won't stay on CPU forever. So the process A gonna go away. So the kernel abstract that counter, say, this is not a Intel counter now, this is the counter my kernel provided. And that's where kernel take the chance to read those counters. But in theory, like you read the counter itself, it's one instruction, take about 20 cycles, you get a counter. Yeah.
Gotcha. All right, fine. It's like
right.
a CSC.
So speaking about the overhead, so what can contribute to the overhead is basically this: the sampling frequency, whether you multiplex between multiple events in the same run, whether you do like fancy kind of things like you're collecting stacks while you're sampling, like for example when you're unbinding the stack and all this stuff.
It's totally where I've gone in the past is, on a timer tick, go sample stack plus a bunch of other things.
Yeah, sure.
didn't grab all the PMUs, but we're able to grab some on custom hardware. But on x86, sample stacks, absolutely.
Yeah. So
also, as a user, I cannot do that. Say I'm in the cloud. I need support from the the privileged software. So unless I allow
Rob has a lot of experience about that now. So maybe Rob can share some.
The reason I'm saying this, sometimes I get these proposals, I'm reading a paper and, we can take this feedback from the performance counters, and then they're doing something in the cloud. And I'm like, there are security implications. You cannot just, develop something on the client side and assume that it will work. You will have the required support from the cloud to monitor your, it's a shared server.
So you can actually use performance counters on cloud instances in AWS at least. Yeah, so what Amazon does is on their newer, on the really old instance types, they don't support it, but on the newer instance types, they will give you access to the performance counters if your instance covers an entire CPU socket. Does that make sense?
Yeah.
So if you're sharing a socket with if you're sharing with another tenant, then you don't get performance counters because they're worried about information leaks. But if you occupy an entire socket, you can get performance counters, and we use that all the time.
Right, but
so it does work.
I think this is a limitation, kind of, because assuming that you're not sharing a socket with somebody else is kind of a.
Yeah, I mean, it depends on what you're trying to do, I guess. Like if you want to have, I mean, it's a limitation, but it's not too bad. I think Microsoft has recently added performance counter virtualization to Hyper-V. So I don't know what kind of support they have in Azure because we don't use Azure, but I think at some point you'll be able to.
There's no
performance counters in Azure as well.
There's no support as of today.
You have to ask for
okay.
overhead of the virtualization or getting at the counters, because that goes straight to how fast you can sample. If some guy says, I'm going to virtualize the TSC register, which totally happened to me, and it went from 1 clock to 10,000 clocks, suddenly it couldn't be used in a major benchmark for which it was being used. Exactly the kind of stuff we're talking about here for the user process of self-optimizing.
I'd like to see the rest of the slides, and then I'd like to make some comments.
Sure. All right. Yeah. Let me move on.
Yeah. Sure.
All right. So if you want to manual collect the counters, so what you basically have to look up in main manual in the SDM's software developer manual. In the chapter 19, there is a whole bunch of performance events for all the CPU architectures. So every event has the event number and the mask value. So you simply put this in a perf stat command, and this is the way how you collect it manually. Well, hopefully, most of the events have their mappings, sort of a human readable mappings for, so you don't have to memorize those, you know, codes on or look them up every time. So you just can say, for example, perf stat -e branches. It will be the same as what I did here on this slide. Okay. Right, and then. So actually, so the last slide I have today is the slide is the idea that you don't have to really know you don't really have to know about performance counters a lot, because you know there are hundreds of different performance events, right, in a modern system, in a modern CPU, and it's really hard to understand their meaning, because to understand their meaning, you have to be an expert in particular CPU architecture, because there are like a lot of strange of data structures and buffers in a CPU, and you have to know how they interact with each other. So there is a cool concept called top-down microarchitecture analysis. And the idea is to abstract away all the knowledge around the particular performance event and provide the top-down approach instead of bottom-up. So because when you are like trying to understand particular performance event and trying to collect and see how and see, for example, some absolute number for your benchmark, well, it could mean nothing to you, right? Because knowing just absolute number of some performance events, well, I mean, it's good, but it doesn't help you much. So this idea is that you try to characterize your workload by first identifying the bottleneck, the CPU bottleneck at the high level, and then you sort of drilling down until you get to the real issue, the real root cause. So, for example, this is the micro architecture spallation analysis for a real world benchmark. I think it's from some compression workload, probably 7-zip or something like that. This benchmark. So here you can see we have like okay, a lot of branch mispredictions. So yeah. So this is I don't have more slides on this, but probably I should have added a little bit, because this is such an important concept.
Just go with what you got here.
Actually, so this is the last slide, yeah. But yeah, so the idea is that so this is an iterative process where you first characterize your workload, then you actually sample on particular event, which will get you to the point in exactly location in source code where those events are happening. Okay, so for example, in this case, while I see that this benchmark has a lot of branch mispredictions, I will sample on branch misprediction event, which will point me to the line of code which actually generates those mispredictions, right? So then I can go and try to fix this. I can try to eliminate this branch. I can try to do other things. So yeah. All right. And I think actually that's all I have. I have a backup slides for collecting call stacks, but since you guys know all this stuff, I probably should have been prepared something more, you know.
No, I think this is a good seed for a nice discussion, and this goes back to some ideas that I started working on a number of years ago that actually got surfaced in Illuminate, which is our productized version of what's going on, and that really is a view of taking the hardware counters and some other bits of information, but basically feeding that back into an AI engine that does the diagnostics for us. And so it's been working reasonably well in the sense that we can come up with a reasonable diagnosis. It generally takes about in the neighborhood of like about 10 seconds to complete. Of course, we can get that much more efficient by doing some things a bit differently. And just we haven't gone back to
what are you diagnosing for here, Kirk?
Well, actually, so what we're looking at, we've actually put this in live systems, and we have this on-prem and customer sites. So we're just looking at if you get any types of performance regressions happening in a system, the assumption is that performance regressions come from too much pressure on one of the underlying resources. And so what we want to do is understand what that pressure is. So, well, actually, it's either generally too much pressure, or there's some sort of starvation happening at some level, right? So,
so like
so what we've done,
memory bandwidth and garbage collection, or?
Well, you know, it could, the hardware counters are giving the clue as to what's going on, then you have to interrogate at a different level. So it's like, it's not a single step process. It's a first getting a global understanding of what's happening. So, I mean, there's a few ideas that we bring to the table. Like first, the hardware is basically your currency in this whole system, right? And so if we're looking at like one or multiple processes or things, all the stuff happening on the box at the same time, then what we're saying is like the aggregate consumption of hardware. Well, the consumption of hardware is going to be the result of the aggregate aggregate of all of the processes. So, you know, whatever they're trying to consume to get it, whatever it is that they're trying to do, whether that be efficiently or inefficiently. So if we get to a point where you end up with regressions, then at that point, what we do is look at the state of the hardware counters. And so there'll be like a basket of them so that we could understand what the potential ratios are between them and things like that. But we'll just basically take that basket, run it through a random forest that we have trained. And the random forest basically comes up with a high-level diagnosis. The high-level diagnosis is then used to fine-tune or aim the engine to basically come down and basically say, okay, now what's really happening up in the code level, so that we can point developers to, you got a problem here, you got a problem there, you got, you know, effectively where the problem is. And
you, for that one, for that prediction engine, can you be accurately like point out the corresponding code section, for example?
Yeah,
like
yeah, absolutely. And I think our worst F score on this is around 87, 88% or something like that, or score of 87, 88, not percent.
So well, I guess I'm asking, what are you predicting?
We're not predicting anything. We're observing. So we're trying to find is like the source of the bottleneck or the regression.
Right. I'm asking, what kinds of things do you get a report back on that you go action further, obviously, but what are you getting out of your AI?
What we're getting out of it is we're getting, you know, basically what, you know, is it a memory problem? Is it an hot execution problem? Is it some sort of inefficient interactions between client server type arrangements? So, and I'm using client server in a loose sense. In other words, we would consider the application to be like a client of the operating system. So we'd look at that sort of interaction also, potentially, or any other hardware device or anything that's going on. So basically, we just want to find the primary bottleneck. Well, we want to find the bottleneck. Now, there's a lot of assumptions in there. So one of the assumptions that we're going to make, like that you're making here, is that you have what I consider to be almost monomodal execution, and there's no there's no modalities in the execution. And so what I mean by that is that it's like the signal going through the system is really just like constant. So that's why you can pick up, like, you got like a bad speculation and you can find the code very quickly, because, you know, basically I got like one hot path and that's being executed, and you know, that's basically one mode of operation, right? So if you get in a mixed production environment, then basically what I'm doing is like the consumption of the hardware is going to be like the sum of all the modalities that are executing with the different processes running on the box. And so the other thing we have to do is sort of like tease that apart to understand, do we have something that's an aggregate because we just got a bad mix of processes on the box? Or do you actually have one process that's actually misbehaving? And then we have to like deep dive into that particular process to understand what's going on. So, you know, the issue we have actually now is getting at these counters in containerized environments. And the fact that now some of the containers are like virtualizing them and picking them apart. So that, you know, we're getting like slices, or they're trying to estimate, okay, that process gets these things, that, you know, and to me, that's sort of like kind of disruptive in the sense that I think people like to know on a per process level, but we're really interested in knowing the state of the hardware, what's happening at the level of the box, so that we can understand what the primary resource contention is on the box, so that we can tease it apart to understand, you know, who's contributing to that particular.
So you're looking for the sum effect across all the processes running where the user's application involves multiple processes. They got a MySQL, they got a Java server, and they got whatever else running on the same box.
Well, we don't care if there's one or many processes there. We want to understand what the contended resource is, and then we can tease it apart, right? Because, you know, the thing is like, you know, you're always going to be limited by the bandwidth or well, the throughput bandwidth, whatever you want to call it, of the hardware, right? The capacity of the hardware. And so if somebody throws like a dozen processes on there, and we basically you know, we put too much pressure on one aspect of the hardware, you know, that's one thing we'd want to recognize. But if it's just one process that's actually putting that pressure on, then that's another thing. You know, the fact that we have different modalities occurring and that applications can switch very quickly between a variety of different modalities in terms of the signals that they're producing. You know, that's a complication. That means you need to, you know, sort of get in there and sort things out rather quickly sometimes. But, you know, that's really, I think, been our use of hardware counters over the last, I don't know how many years, like, you know. And so we actually haven't gone down to programming the MSRs in Illuminate, but we do have another open source project that I started like, I don't know, many years ago now, which was JMSR, which is basically like, again, understanding how to program each of the MSRs on each individual chipset so that you can get performance counters out of the MSRs.
Okay, so what counters are you using? What counters are you measuring?
Right now we're basically just limited to a breakout of some of the very high-level CPU counters and some of the other counters that give us indications of like bandwidth, like memory bandwidth and things like that.
Yeah. I mean, LZ, whatever, 7-zip here probably has mispredicts, but I bet most of your apps have bandwidth issues and not branch mispredict issues.
Right.
Yeah,
this is just one example.
Yeah, and really what we see is that the bottlenecks will be on the front end. You know, be front end bound. It's basically because you can't feed fast enough because of, you know, whatever reasons. So we tend to find those in a vast majority of our applications. The other common problem is just starvation. So you'll be starved of some resource. So we'll tend to focus in this case and say that you're thread starved, and the thread starvation may come from, you know, I simply don't have enough of them, to something more complex that they're hung out, either on a lock or on a call to an external system or something like that.
That's not using performance counters per se.
No, that's not using performance counters to find that, but we actually will identify that situation from the performance counters, because if the performance counters are in a situation where we have regressions and we find the counters are basically quiet, then that's another path that we go down to figure, okay, why are the counters quiet?
Are you able to get contended lock numbers out of whatever JVM you're using?
Yeah, we can tend to find hot locks if there's a hot lock.
Well, okay, so hot locks, and yeah, okay, fine. Yeah,
That's pretty easy. You know, those things are pretty easy. It's some of the harder things to do are just simply identifying, okay, you know, like I got threads stuffed up waiting for downstream calls to complete.
Right. No, they're
because
blocked.
now you have to get into knowledge of like a higher level knowledge in order to be able to do that. You can't simply do that from the hardware level. So yeah, so we've been using, I guess, this reduced form of AI for a number of years to do all of this performance work. But you know, the really issue that we have, and the thing that's really starting to hurt really badly, is that we just don't have access to the performance counters anymore, because simply because the containerization is basically locking us out, and the containerization as it is for some of the numbers we can get are giving us like funny numbers, and so we have to train for these funny situations where we're not getting raw numbers, we're getting virtualized numbers, and the virtualized numbers actually come back and they make it a lot more difficult because they really hide from you what's happening at the hardware level, and we really want a pure hardware picture as to what's going on, so we can understand what the state of the hardware is, so that we can understand how to unpeel from there.
So for the container, there are also two perspectives of the problem. One is the virtualized counter, which is like in theory, everybody you can support very well, but no one has done that well. And second one is the Linux kernel's problem, because the C group, a lot of containers use C group.
Right.
And then which means you on top of the process, you have another C group abstraction, and the kernel haven't done a good job in terms of like keeping the numbers correct and low overhead for all those C groups.
Right.
Those are open problems.
So full disclosure. So Microsoft bought us last year, about almost a year ago now. So we're actually trying to figure out how we can get access to these things, because really we only need one little thing running per machine. We don't have to have, it's not like we're running an agent per JVM. We're not doing that. We just have something running someplace on, that has access to this, that can understand what's going on and can actually reach all the JVMs individually if they need to.
But what I'm hearing you say is you're begging for better support for the performance counters in containers.
Yes, that's exactly what we're doing. We're talking to the container guys within Microsoft. It seems like the trend today has been a continuation of the trend as forever, right? I don't actually know what I need to collect, so I'm just going to like grab a bag of counters and hope they're the right ones, right? So when a problem shows up, I think Cliff and I we've already talked about this before, Jcrete. So basically you get like a Grafana spattering of random counters that may or may not be meaningless to your current, may or may not have meaning to your current context and stuff like that. So what we're trying to do is sort out counters that are actually meaningful for the context, but in order to do that we need to understand the context, which means we have to grab other counters that we run through the random forest that actually say you're in this particular context, you're in that particular context. So basically what we've tried to do is derive a taxonomy that helps us categorize things. And so we use the random forest to actually drive us into this, to categorize these things as defined by the taxonomy. And then the downstream actions depend upon where I end up in this particular taxonomy.
Just one question. So why are you just grabbing the whole bunch of different performance counters? So are you actually familiar with the top-down methodology? So the slide that actually I am now presenting.
Well, the top-down micro architecture analysis, yeah, somewhat. So we do sort of the same thing.
Okay.
Okay. So this is something that we've been doing like for years.
Right. So this actually, right. What I'm saying is that this actually allows you to really cherry pick the small number of counters and sort of a drilling down until if you wanna get more sort of a specific knowledge
Right.
about the underlying root cause, then you're drilling down. If you are just okay with, okay, my workload is front-end bound, you just basically need to collect, I think, 4 counters, and that's it.
Yeah, so I understand that, but what you're saying is that this top-down is too slow.
Top-down is too slow. Well,
Yeah, so by the time, so if you're trying to catch certain modalities, then, you know, by the time you get through this analysis, that modality is cleared out, the symptoms are gone, and so you can't do a diagnosis anymore.
all right. You will probably have better support in new CPU generations. In Ice Lake, you will have them for free. You will have top-down analysis for free. It will be.
I mean, these things are really cheap, so that's not really the you know, I mean, it's really cheap.
Saying that you want to figure out that I'm in a memory bound or a branch mispredict bound zone, then turn around and change what counters you collect.
Yes, that's exactly what we do.
Within a time window that's short enough to catch the rapid cycling the applications are going through.
That's correct.
Yeah,
that's precisely what we're doing.
So you may be interested in one of my papers where what we try to do is we try to build a high fidelity of how to observe program behavior and every high frequency. So what we do is we put an observer on the same core, but on a different SMT. And that guy is like a little spy and read the PMU, like every 20 cycles, every 100 cycles, you read what happened, and then you look your software. Like you read the counter and you look your neighbor, where's your neighbor? You look your counter, look neighbor, and so you can build a very, very high frequency correlated information about performance counter and some other software signals.
Yeah. So I mean, our sampling rates right now are in the our initial sampling rates are very slow. We're not talking about high frequency sampling. We're talking about low frequency sampling, and the rates of hundreds of milliseconds or seconds.
Yeah, so we basically do like sampling rate every you can do like every 100 cycles.
Yeah, something like that.
You can get a very accurate correlation between the pathology, which, for example, you get a high catch miss, and you can quickly know where your neighbors is running on. Yeah, but that one has a challenge in terms of like you can quickly collect like terabytes data, and how can you analyze them is becoming quite annoying.
Well, so that type of problem we solved. We can analyze these things very quickly. We don't need a lot of data, right?
Yeah.
We just need data that's not been, you know, adulterated by or deuterated or basically fudged up by different systems mucking it up. You know, so so when we're getting the pure, if we're running on bare hardware, and we're getting like the pure counters. You know,
do you also understand? Also, at the same time, you collect a lot of other software or system informations, like who is running, and so you just use the.
Well, we don't actually collect that stuff until we need to. So a lot of this is because you know, you think about this like like if you look at the issue, like we need to scale across like I don't know LinkedIn as an example. Right. So we want to scale this across LinkedIn, right? So if you start collecting the amount of data that you're collecting, we're finished. That's not going to happen. So,
so that's basically, it's like you detect some regression first, and then you go some diagnose.
Yeah, exactly. That's pretty much it. Yeah. So
cool. So you can also like kind of like track, for example, if there are like 10 commits, you run that for each commit, and or maybe 10 deployment, you just track.
Yeah, we have a lot of sampling in there, and I think, you know, that we can get away with that simply because it's like not a trading system where everything has to be bang, 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 bang. But for a lot of these systems, there's enough room in there that we can actually just go with very, very low sampling rates, and that's good enough. Right. So we're not trying to build the perfect thing. We're trying to build the good enough thing.
It's pretty cool.
So you have a lot of producer-consumer relationship things going on there. You do anything with tracking the flows between these different things?
No, that's incredibly hard. So, and not necessary.
And not necessary.
And not necessary. No, if you this is a problem. If you stand it on its side, you actually get better results a lot cheaper. So we're actually more accurate than people are at finding primary bottlenecks.
Okay, fine. Yeah, fine.
A lot more accurate. Actually, we're finding things that I have to spend like hours explaining to people like why this is their problem and not what they think their problem is their problem.
Been there plenty.
Yeah, yeah. So you know what I mean, right?
Yeah.
And so like the engine will come up with the answers and they'll look at it and go like, that doesn't make sense. That's not what we expected to see. And they're saying, well, that's because, you know, everything else that you have is actually heavily biased and it's not allowing you to see what actually, you know, the problems are basically invisible to you, right? So you can't hide from the hardware counters unless they start hiding them from you.
Unless they hide them from you, yeah, right.
Yeah.
No, that was mine.
Right. Or they do, or you do something to them to like muck them up.
Yeah.
But you know, I try to give people the idea that they need to look at the machine as like this holistic piece of something, and you can slice it up, but you know, you can't slice it up in, you know, infinitum, you know, because afterwards you just run out.
All right, let's change what we're talking about here. I think we beat this one down a bunch.
Yeah.
I hear there's a need for high fidelity tooling, which I totally get, and I totally agree with. We got somebody else have any questions? Chaim, you had a particular, you were here for a reason. Do you have a question?
Yeah, I'm trying to do some kind of a bootstrap or bootcamp of how to use these tools. Okay, so I'm trying to understand how to use VTune, but with not a great success until now. I'm not sure that I really understand how these tools are working, like how to work with perf, how to work with VTune.
How to read results or how to actually?
No, how to actually operate with them. Okay, so I'm trying to run it on my Mac. I don't know how to install it on my Amazon Linux machine. So maybe it's newbie questions. If you can send me to documentation to read, it might be enough, but.
Well, I thought perf stat was pretty clear. Is that just normal Linux distro?
Okay, so in order to install perf, I was able to do that. You need to yum install. I'm talking about my Linux machine on Amazon. So now I have it on my machine, and I can use it. I see that I need to run a command line in order to analyze it. I didn't understand if I can attach to a running process, which might be in some case a better.
Like it sounds like man perf.
Yeah, really, like a man perf. So.
I know these things can be done on a running process. I just don't know what I don't know what the story is either.
Yeah, for VTune it's pretty easy. There's just a command line options you can use to basically have the agent run with your JVM, and it'll dump a file, and you just take the file off and use the visualize, you know, the other end of the tool to visualize the results. So you get this fancy little diagrams like what's showing up on the screen here as an example.
So it's an agent running with the JVM.
Yeah, that's one way they run it.
And it doesn't attach remotely. You just take the dump and put it.
Well, that's the easiest way to do it. If you're in a cloud environment, just run it and it just get dumped file, and then, right? Because if you want to run GUI tools from cloud environment, you need to get into some rather complex tunneling and crap like that. So it's just, it's easier to run headless and then take the file and then just read it locally.
Okay. I have a situation now that I have a process that is consuming a lot of CPU. When I try to use YorkIt, which is usually my favorite profiler, I know that it has its limitation. I find nothing. It seems like there is nothing to
So you find nothing, meaning everything is idle and it's not reporting anything?
No, it's not idle. It's either reading from network, either from other services or from the database.
And it has a high CPU load?
Yeah, it has high CPU load.
So, yeah, so do you know the high CPU load, what the breakdown is between the kernel and user space?
X load.
No, but yeah, no.
Yeah, on your Mac,
that.
you can just.
Oh, it's not on my Mac. I need to run to see what happens on.
Yeah, if you
on
if you just run like a straight VM stat out of the box, it's generally good enough. It gives you a reasonable breakdown.
Yeah.
And then you can understand, you know, where it's consuming, because normally what we see is like if you have a high CPU load on something that's utilizing the network a lot, then basically it's typically a situation where you have a revolving door. That's a performance anti-pattern. And the revolving door in this case is basically you're just like constantly context switching, taking like a byte off a network out of a network packet, processing it, and then going right back onto the network. Right? You get like, if you get a pool of threads doing that, you're just going to like drive the kernel batty, and your application is not going to make very good forward progress.
So if I see high kernel load, then that's probably the situation.
Yeah, so hang on. So there can be lots and lots of proximate causes. Maybe doing the diagnosis over this group is not necessarily the good answer. Kirk's had a lot of experience in this space. Other people have as well. You might talk to us and see if you can figure a time to do a sort of one-on-one, and then you can start getting these tools. Like the first thing that happens with these tools is you get some data back that steers you in a direction, but the expert has to come along and help you steer if you haven't figured out where to go yet. And then it's a feedback cycle with the person involved. So I'm saying, let's not do an app diagnosis on the spot.
Okay,
sure. Get the basic tool going, but now drag somebody in when you can be in an interactive session without 10 other people hanging around.
Okay. Yeah. Actually, also Vitun has nice platform view where it allows you to see what each process was doing during particular time moment. So it's really nice. I like to use it as well.
It is a nice view.
Different people still wandering in and out. I don't know.
So Cliff, when you got a chance to design the huge, what was it called? The huge box. Yeah. Did you, because like a lot of these issues that people like us, we don't have a chance to design the PMU, to make a lot of PMU designed by the hardware architecture who don't understand a compiler, don't understand how to do good profiling. And did you get any interesting stories, interesting experience while you were working?
Yeah, sure. So, yeah, right. So PMU is like way down on the priority list, right? The first thing happened is the hardware guys had all sorts of cool ideas of how they're going to make Java go faster that were completely misdirected and totally useless. So I had to shoot down a lot of cool custom hardware that was not going to actually help. And then the normal stuff, the JVM jits well to a good jitting target. So the first order rule of thumb here is just give me a goddamn easy to JIT to target, right? So give me a good 3 address classic risk. Then there are some minor hardware instructions to speed things up that were modest tweaks for modest gain, and they were like range checks built into loads and stores on arrays, and read and write barriers built into load and stores off of pointers. The proper scaling math, Intel does not do the proper scaling math for long math arithmetic for Java. So it must require an extra instruction to mask before shift that you didn't need to. Stuff like that was going on. For the actual PMU kind of behaviors, we had a couple basic counters. That's all we really needed. And we had hardware transactional memory, which we could cover a lot of other fun ground with. And the other thing was we did what you were talking about with your stuff. You had a lot of cores. So you had a neighbor you had somebody hot spin and watch things. So when we wanted to do like instruction tracing, we could catch basically real-time instruction traces by having the executed instructions flagged by a core going out to the L2, which was getting flushed from one L2 to another as fast as possibly could be. And then from there, from a remote L2, it went off to main memory and eventually off to disk, and you could squirrel them away. So there was some slowdowns involved there, but not very many. So we basically could get actual live full speed instruction traces by burning a bunch of cores and a bunch of L2s. That was way more productive. Then you get these billion instruction traces. So we did a whole lot of analyses on billion instruction traces that we got, within the first few weeks after we had real silicon back. Well, it took a little longer to get not too long after get the real silicon back, get the bugs out of the system and whatever. We were getting big instruction traces. We didn't do fancy PMU. We didn't sort of have the silicon or the engineering manpower to build it, and nor really the need. We had basic, obvious problems. So having huge count of cores and not enough engineers and an older process meant your cores were really simple. So there wasn't a whole lot to measure. The first chips were single issue in order, with one hit under miss. You could throw a miss out and then you could carry on until the next miss and then you were stuck. It wasn't until the second generation you could get 2 hit under miss. But 1 hit under miss was like a big win, but that was more important and more obvious than having the PMU to diagnose all kinds of other fancy things going on, because there just wasn't that much.
So the system is also more like in terms of like microarchitecture level is more like performance deterministic. Like you can
very much so.
You get instructions counters, and then you get count instructions. You get exactly know roughly like how long it takes.
Yep. There's branch prediction, but there was no.
But did you consider like the one you mentioned that going to be? I guess that would be super helpful when you see some weird problems, but when you're debugging the low level stuff, right? The instruction tracing of those stuff. So did you also get chance to design some hardware assistance, like maybe not PMU or maybe other hardware profiling or tracing features that you think tremendous help?
You can do things here that maybe people don't think about or haven't thought, whatever. So we get these big traces. We go start looking at why. We run them through a simulator, and then you ask ask the simulator, why are we getting all these misses or hits or whatever. Turns out that the first cut had all our stacks aligned on the same high power of 2 granularity, which meant all the stacks had their leafs where they're running up and down in the same lines in the L2. And we had 8 cores.
Trashing.
Yeah, on a 4-way L2.
Okay, stack trashing,
Yeah. Cool. And so it just needed random stack coloring was worth a big win. But that showed up right away after we ran the instruction traces through the profiler. Well, through simulator, and then got the profiles out of the simulator. So the next thing that happens is you throw them up on a pretty color chart, and you see what lines in memory are bright red for constantly missing or not, and it becomes obvious, the stack's hammering. Then we go back and you look at your L1 and your L2, and you could see, color coded for heat. If you got cold sections of your L2, no one's touching those lines. You got hot sections, they're overcommitted. And then you can work backwards and see which threads. This is all multi-threaded everything. So you watch which threads were doing what, and start to recognize the patterns. It's sort of like what Kirk was talking about. You had not one thread doing one thing. You had a bunch of threads running, and then they interacted, and you want to know what the interactions were. We collected big instruction traces and ran them through a simulator after the fact.
Okay, but do you have any help on the, for example, that machine support the hardware transaction and it can be aborted, right? Because, and do you support something like help you to help the team to recognize this abort is because this reason or because that reason, something like that?
No.
So you just
the answer was You threw down as much cookies as you wanted to throw down before you started manipulation. And then you took a user mode interrupt, and at the end of the, the hardware playing its little clean out game, you were back to where you had started as if nothing had happened, except that you got one or two, like a couple different tokens out of the hardware for why you had fails. But the common fail was you evicted a line. And that was your reason for failure. So we kind of went back and forth with hardware guys. Can we have some lines that don't get wiped out? And they're like, that's another change to the silicon. We don't have the budget to do that. And it's really easy to like screw it up because that blows out the cache coherency protocol. So the cache coherency protocol was, 800-way machine being cache coherent. And a lot of, there's a lot of magic going on under the hood. The HTM basically sidestepped that by not allowing anything to write out of the HTM, or the HTM blew out and then cleaned all the lines out and validated instead of writing anything. So it basically just ran away and hid from the cache coherency protocol, which meant you couldn't have anything sticky. So you got one or two, and it wasn't two, you had some small count of bits that came back from the HTM when it failed. One of the failure modes we could tell was we took a TLB miss, which we would just reload the TLB. It was a user mode TLB, which is reload the TLB and go again. There was another miss that was a little harder to diagnose, the hardware would tell you about, but the most common failure was you wanted to dirty a line and somebody else wanted to read it, or somebody else wanted a dirty line that you had read. So you lost a cache line under speculation, and that was it, you were dead. Now, what line and why, you didn't get.
Yeah.
So we could argue that, I would have loved to have had the cache, the physical address even, reverse it to the virtual address of the line that blew out. Because then I could go back and tell you what Java object got touched and where it got touched that caused me to die, right? But I didn't get that. I don't think I got the program count. I might have gotten the program counter on death. I'm trying to remember now if I did. There was, mostly what we did on death was after we diagnosed and fixed some of the obvious stupid things like page coloring for the stacks, the HTM was mostly, you tried it like a spin lock. You tried it a few times and you gave up and took the lock the hard way. And then we diagnosed some of the repeatable HTM failures where we thought we should have been able to succeed, and discovered that people in Java wrote true data dependencies for junk performance counters, and that blew you out. The moral of my story there is transactional memory by itself will not accelerate anything, any old code. That you have to write transactional memory friendly code to make that work. And as a consequence, you're writing code that's friendly to being executed in some other context. People went and did that a different way, and that's called microservices these days, right? You just put in a different process and you make yourself process tolerant. Processes come and go. I try again on the shared server that has lots of these processes. Some of them are live, some of them are dead, some taking GC pauses. There's a solution there for an unreliable, more difficult one. But the HTM for like concurrently running code, you have to have a different coding style, and you have to have feedback from the HTM into the programmers to recognize when they've varied off from that style and they're not writing code that's not HTM friendly, and therefore it will not run parallel. So, I had a fun learning experience there, and the main lesson is, services provide a disjoint parallel concurrent execution at a different granularity than shared memory hardware. And therefore you get some real concurrency that is difficult in other contexts. The other downside, of course, is that there's huge inefficiencies in them damn microservices. And so I still live in the world of concurrent programming, but I don't try to sell it to the masses as a solution for everybody. You have to rewrite your thinking, and you have to rewrite your tool chain to be HTM friendly. And what Intel's doing with small count HTM is pretty reasonable in that world order. You know, we went for the everything's in Java, it's going to run concurrently model. And so we were expecting to see lots and lots and lots of big transactions that were big and sloppy because people weren't thinking about it. And what we found was lots and lots of big transactions that were big and sloppy and had true data dependencies for no good reason. And we couldn't work our way around the true data dependencies. And we couldn't ask everyone to rewrite their code.
For those cases, what do? You just disable, for those ones, just disable.
Yeah, we just put heuristics that had timers on it that counted fails and gave up. So the hardware was in there and functioning and working, but the number of times it accelerated a lock was too small to be worthwhile. So it took a while to get it turned on and running, just because we were, you know, we had other fish to fry for quite a while. But eventually, you know, when I left, before I left the company, it was up and running in the standard default, you know, build for everybody and not being very helpful. A lot more mileage from the garbage collector. Garbage collector one big. That was another one that you got out of the hardware co-design. The garbage collector issues. Some of it was just regular old software stack hacks that's in the Azul x86 implementation now. Some of it was fun stuff with garbage collector in mind. Your read and write barriers was part of that. The other one was just recognize you have lots and lots of cores and you run the garbage collector on a different L2. The garbage collector is going to thrash your L2, right? It's going to have horrible locality no matter what. So don't bother. You put it off to the side, and then it trashes some L2 somewhere else. And
that's problem with ZGC now, even though they have a fully concurrent GC, but because you don't have the hardware to help you to control how strong you're trashing each other.
Yeah. So, well, that's an OS issue, right? You want to say I am a garbage collection thread or I'm a mutator thread, and the OS preferentially places you on CPUs and L2s apart from each other. Like if I have a big busy box that's doing lots and lots of other real user mode processes and also running concurrent GCs, all the concurrent GCs could all be running on the same L2 because they're all going to trash the hell out of that L2, and it just doesn't matter, right? And they all should be running in the background and keeping up slowly, but keeping up. They have no time performance sensitivity in that sense. So they need one L2 for them all. All processes can share the same L2. This is an OS level issue, which we sorted out in RS. But you have to have a custom Linux kernel hack to get it on the, you know, sort of a Linux thing, which Azul, no one from Azul's here, I think. But Azul totally, when they go to the low latency traders who really, really, really want low latency, you know, they do a whole lot of Linux kernel tweaks. Nothing that's custom per se, but there's a whole lot of tweaks you do to the kernel to make it friendly to low latency. One of them is you jam the GC on other cores. You get it off of the main mutated threads.
But you can do that without modifying the kernel, right? Because they give you affinity API, so you can pin particular processes and threads to particular cores. That's
what I'm saying. So they do a lot of tuning, and part of that is some of it's like you can't be zeroing pages because of it like interrupts whoever's doing something, and you can't take interrupts obviously, and there's like 15-20 other random Linux kernel tweaks they do to shave the latency off of the important mutator thread who's also reading the network packet sort of in DMA hardware land and doing bizarre things.
But one of the quite weird, those kind of like pauses, interesting pauses recently we hit, which is when you have a Java and you have a huge page enabled on x86, and same time you turn on the deep sleep. So what has happened? You turn like you wake up you're gonna be a lot of like your service receive a lot of requests, right? A lot of Java thread wake up, start to handle this request, and everybody gonna do the allocation. At the same time, they touch the page fault. So everybody drop into the kernel, say, I have a page fault, I'm 2 megabytes. And the same time, the kernel just wake up from deep sleep, and everybody is very busy. Like you have your catch is, you have no catch locality. and the kernel does a zeroing first for the 2 megabytes you allocated. So now you have a lot of cores, each one asks 2 megabytes page, and kernel has to zero them. And then the CPU is very clocking state. So you can like we saw that very, very slowly zeroing inside kernel for like 10 milliseconds.
Yeah, that's the Azul tweaks to make sure that doesn't happen. That's some of their tweaks. Because they're very familiar with that particular behavior.
Did you do some special prefetching for the GC for the one?
Yeah, right. So for the Azul hardware, nothing to do with x86, we have a special prefetch for GC. Yeah, for the mutator threads. So it's a cache line 0 prefetch, but it has a different fencing than the default fencing, so that it could prefetch through a lock that would otherwise block it. And that's crucial because allocation and locks intermingle. And so you have to not have a cache line 0 that is cache coherent and then memory fenced by locks. So the cache line 0 had a separate fencing instruction.
As a mutator sign, right?
The mutator would run it, and the mutator would issue cache line zeros, some number of cache lines ahead, and when it was done, when it was ready to go use a cache line for the Java process, he would then fence its coherency protocol so that it wouldn't let you publish a line that had random junk non-zeroed to another core. But that meant the allocation path bumped pointers, but it watched cache lines, and it bumped the pointer on this cache line until it ran out, and then went to the next cache line. But when it advanced the cache line, he prefetched some lines ahead, and he zeroed the line he just got, and then he was able to go fill it with whatever. And that cut a third of the total bandwidth of the box off. 1/3 total bandwidth cut off, because it didn't have to read the 0 from memory or L2. It just put the 0 in your L1. That was a giant bandwidth savings. So that was one of the many fun hacks in hardware. We had supercomputer level bandwidth, but also we burned 1/3 less hardware than an equivalent x86 process, as totally measured with ICE and whatever the hell people were doing.
That's some sad part about the PMU design is that PMU is actually can be quite important, quite be useful, but because it's really not a high priority for both the core.
That might be changing here as people begin to realize. I think one of the large lessons from the whole Java experience is that a continuous cost overhead of 1% or less for profiling will pay back much greater dividends. It's totally worth it to be. So it's why we have nerve cells all over the place in our bodies, right? A little tiny bit of feedback everywhere beats the hell out of just balls out to the max speed, but blindly, right? Drag strip racers can run in a straight line really fast, but they cannot take a turn. Yeah. You want to have a little tiny bit of profiling always, and available at all levels. So user mode, kernel level, people can use it. Totally, Azul, x86 Azul will do stack trace tracking on a regular timer interrupt. Collect those stack traces because it's just too freaking useful, and the cost is low enough, you pay it. And if the costs are lower, we pay it more often. It's got a real cost, so you throttle back on the interrupts, but it's totally worth it to hand somebody, the stack traces to go with their timer interrupts. I don't know, that's for me, that was the thing that was new and different, that I still see people fighting. I'm with you on this. PMUs and something like it are important, and they should be available readily for everybody in every process, and we have high fidelity. Kirk's fighting the high fidelity issue, but we fought for a long time to get them at all. You don't need a whole lot. They don't have to be very expensive, but
I'm not fighting
you
high
user
fidelity.
mode.
I'm not fighting high fidelity. I'm just saying we don't need it.
No, not high frequency.
High frequency.
You're getting answers screwed over because you've got containers intercepting.
Oh, sorry, I misunderstood what you meant. Okay.
Yeah. I'm not talking about high frequency. I'm talking about high fidelity.
Yeah.
Yeah, you want to know what you know as opposed to know it super high detail or something. I don't know what the right analogy is.
I mean, the thing is, like, there's a lot of information you can get just by by proxy. So we don't need direct measures. We just know that, you know, that thing can't happen unless you have these things happening over here, right?
Yeah.
And so there's quite a few things that are happening like that that we can just detect. So we, you know, so we don't, you know, we don't need a lot, but what we need, we need.
Yeah. Yeah. Yep. I get it. So other things that I would love to see out of PMUs is some way to dump the current state of an L1 cache, flush it out as a bulk thing to an L2, and then carry on with life. And let me scroll up from L2 to memory and go on. This is a snapshot, profiling snapshot. And the reason being is one of the things I got out of the shenanigans we played at Azul was I could tell you what was in your L1 and your L2 by burning another L1 or L2 or whatever was appropriate to go get it. But knowing what was in that cache turned around and helped me figure out what was not in that cache, but I would have expected to have been. And that was all about understanding what the hell my process is doing. So,
that's a hell of a security hole.
Well, in the case with Zulbox, it was all the same. You know, this is the OS was asking for me, and it's usually run by, it was owned by one company. So that was the limit. All the processes on that box were one company, right?
Mm.
So, you know, you could, same thing as having the kernel, you have to have root permission to go get it, but if you got root, go get it. And it would be useful. So your clients have they own the hardware, it's bare metal, and they own it. Well, they can run root. They run root, they can get everything. Well, why not?
Okay.
Yeah, you know, you argue what you want, but as soon as you own it all, fuck it. This is where your performance goes. Why is it not in my L1? It should have been. Why did it get evicted? What the hell is going on? So having a snapshot in your L1 is like incredibly useful. So that was us diagnosing page coloring, but we diagnosed a bunch of other random stupid one-off events we went and fixed. I don't remember what they were. The first 6 months we had the hardware, we were finding big stupid fails that made things go slow that were easily fixed if we only knew. But we knew, but I'd never had that information before. So I was just like, how the hell would I get this on an x86? It was very helpful.
Another one is that they're going to be quite related to this one. Is one performance problem is very hard to diagnose, but you get performance counter, you know that for a lot of Java benchmark, the instruction cache and also the decoding on those front end play a quite important role. But the PMU the design of PMU really don't help you to figure out what has happened for your level 1 instruction cache.
Do you have an iCache blowout issues?
Yeah. There's a lot of Java iCache issues.
Is it iCache miss or
iCache? So the fundamental problem, because the instruction footprint is huge, right?
So it's iCache miss.
Yeah, iCache miss, and also for XCT they have a level 0 cache, which is another instruction cache.
Yeah,
and that if that is missed, the problem is that if that is missed, it's like you cannot put your whole pipeline can get stalled. All of the resource and backend.
Yeah, right. No, if you can't feed the front end, you can't. You're stuck. I guess.
But you cannot. The PMU cannot tell you what has happened for your instruction, right? It tell you, oh, you have a cache miss. And you have iCache miss, but it does not help you too much in terms of diagnose which what is happening for inside your instruction cache, why you miss.
Yeah, fine. Yeah, okay. Yeah, I quit generating code for Java some while ago. I don't know what Oracle's been doing with it. We watched iCache blowout and iCache misses a lot back in the day. iCaches have gotten modestly bigger, but the code has gotten hugely bigger.
Yeah.
So it could very well be tighter code is faster code, even if it's more redundant in other ways.
And interesting, I found that C++ code sometimes even more crazy than the Java code. A lot of interesting weird patterns in, yeah.
Mm-hmm.
All right. Well,
I think another one is I think Rob doing a lot of performance counter stuff in a different way. Maybe he found some very interesting.
That was an invite to talk about yourself, Rob.
Yeah. Okay. I mean, what we're using performance counters for non-performance applications. So I don't know if there are many use cases doing what we do, but we run into some interesting problems. The main problem we have is that the counters are generally a little bit fuzzy. So you want to count, say, retired branches and or just retired instructions. But what you actually get is a little bit off, right? You'll get retired instructions plus or minus 20 or something like that. And for our use case, that's not really acceptable. We actually need to, the property we need is if you execute an instruction stream and the thing you're counting is deterministic, like the number of branches retired or whatever, then every time you execute the same sequence of instructions, right, you should get the same number.
Is there like a Larish Ball paper on doing this efficiently with just
with code? Yeah, they use code instrumentation, but that's exactly what we don't want to do, and that we use the PMU to do. I mean, there's a lot of reasons why in practice code instrumentation is a bad idea. I mean, it basically gives you an overhead floor that kind of sucks, and then you have to deal with things like JITs and stuff like that. It's much more efficient. It's much simpler and more efficient if the PMU will just tell you the answer.
Well, it probably is, and then you get a non-deterministic variation because the interrupts and TLBs and shit happens.
Well, I mean, you can program the Intel counters at least to only count user level events and to only count events that should be deterministic, that don't involve things like TLBs and caches.
I think in Rob's case, a lot of them are, I'm not sure they are bugs or just because
you said user level, that means that somewhere the hardware decided you were a kernel or you were a user, and so he counted or he didn't. But when the hardware decided or not, and then when the kernel decided you were kernel or not, are different things, right? So some instruction happened, and then you switched to a kernel, and somewhere along the line, an instruction popped something, and some counter in the hardware goes, and then there's a kernel transition, and now the counters get counted a different way.
So
edge case there.
Those things can happen, and I claim that they're bugs. I mean, it turns out, I mean, RR works because on Intel, if you count retired conditional branches, and that's about the only thing you can count that actually has the good properties. But if you count retired conditional branches, it gets things right consistently over a huge amount of. We've done a lot of recording and replay, so it does work. And so they are doing the right thing, tracking. They're doing the right flushing or doing the right tracking.
Doing the right
I don't
thing
know
for some set of that, and not for some.
Yes, but I would like it. It'd be helpful to us if we would like it if more counters behaved.
Don't twist Intel's arm.
Well, I don't have much leverage. It's a big arm, but we are trying to get there with AMD as well, and we're getting close, but they're not over the line yet. They've still got some issues that we're working through with them. Mm-hmm. So these are one of the things that is pretty actually useful to us. It's really useful if the counters are actually like reliable. But of course,
have you got a chance to talk with those guys who work on those counters? What they say?
I mean, I've been to meetings at Intel with people who are supposed to be working on it, but I mean, they've got a lot of priorities, and I get the impression that the use cases where the exact numbers really matter, i.e. ours, are pretty low on their list of priorities. So I'm not that surprised.
And heard that same kind of a story, and I'm not running $1 billion company, so maybe it's true.
Yeah. But that is one thing that it would be nice if there were more applications for exact counter values, that we weren't sitting out here on our own. I mean, it's a little bit scary because some architecture generation, we could just get screwed, right? Like they could just break the stuff, and most of your applications would probably work, but ours would be broken. So that's a little disturbing. But yeah, I mean, I guess the other thing, you guys have talked a bit about availability of performance counters. We don't really have a problem with containers ourselves. That stuff seems to work. Virtualization is kind of like, so I mean, it does work. I mean, I hope that Microsoft, will get things together and provide some solution on Azure, and Google needs to do something on Google Cloud as well. But I mean, the technology is there, and we know how to. I guess I guess someone knows how to do it because it does work on Amazon. So there's some hope for that.
I went through I went through the transition where the TSC register went from not very deterministic on Intel to being fairly deterministic, plus or minus various heat throttling issues, to being virtualized by pretty much everybody, which made it cost 10,000 times more than before and made it completely useless for what we were using it for.
Yeah.
So I think there are different approaches to virtualizing it. I mean, the one you probably got some kind of trap and emulate approach, and there are other approaches where you can just add an offset to it or whatever. You know, like there are low overhead approaches to doing that.
I'm
So
just saying
that
it got shot down and is no longer being used, or wasn't being, when I left Sun, it was no longer being used. But when I was at Sun, not Oracle, we were totally starting out with using the TSC register as a early first program counter, but also in an application specific way that then failed later and we had to abort. That was
one other thing I wanted to mention is performance analysis. I don't know if we've done any work on it, but so we have this record and replay engine, and for straight line code that doesn't call into the kernel, the overhead of recording is essentially zero because we're basically catching all non-deterministic inputs to the system. And because we can do this record and replay with low overhead for CPU bound segments, we could theoretically do performance analysis of a replay. So we can basically rerun the code multiple times with different counters, with different kinds of instrumentation or different kinds of counters turned on, and combine the results, because we know we guarantee we're executing the same instruction sequences on the same memory layouts over and over again.
Your caches are the same layout?
I mean, memory is, we can't guarantee the cache contents are the same because we don't control that, but we are executing the same instructions with exactly the same memory addresses.
Okay. Sufficiently trace, touching sufficiently.
You'd hope that once things are warmed up, that you're basically in the same state.
Yeah.
And another thing you could do is you could run, for example, you could run that, get some performance counter values, then you could rerun those instructions, instrumented with some software instrumentation to do things like cache simulation or whatever. This is something that did you get around to doing this? I can't remember. I've been suggesting it to people all over the place, but
we totally
managed to get around to doing it.
Yeah, I'm one of the students is working on that now. So we got some early system working for Java where we can record and we can for any because how R works is R record your architecture state every time you trap to the kernel or you go to kernel, right? So we get a lot of those points. So we can, when we replay, we can just get performance counters, and we replay it again, we get performance counters again. So what we try to do, actually, we try to use this one to do a cross microarchitecture comparison. What does it mean? That we go to the microarchitecture one, both of my x86, we replay the recorded trees, and we get performance counter. So we go to another one, which is a different microarchitecture, maybe different cache or whatsoever, maybe different, another is in order, another out of order. We run the same thing. Like we get a deterministic architecture state, but different microarchitecture changes reflected from the PMU counters you read. So, and we got, now is that this is working now, but we haven't get to the real stage where we start, how can we analyze those data? And even more interesting thing, but an even more interesting one would be go to that replay place, and then you tell the microarchitecture, say, flush all the cache and run this one, see what happened, right? Yeah, so we have a baseline system working now. We target the conference early next year.
Okay, look forward to seeing that.
Yeah, but now is we have to, this is quite cool, but we have to figure out how to sell this. And what's the, like, you can do this very fancy analyze and why it's useful, right? That's.
Well, so Cliff was asking about how do you're talking about extracting what's in your L1 and L2 cache. With a simulator, you can get that information, but of course the problem with simulators is they perturb your application enormously. But RR gives you a way out of that. Pardon?
So we fixed
Right?
that.
Well, you fixed that with hardware.
No, we fixed it in software. We ran this through simulators. So we did the time warp thing. Like you're talking about, we caught all the non-deterministic things. We caught all the things that gave a notion of time to a running application, including file stamps off of every possible file it would read, every other process, every other thing they would do. We intercepted and warped all the time. So we could run into 10x slower slowdown, and the application believed it was running at standard speeds. Otherwise, it would all transactions would fail for timeouts, right? We're running a big Java app server, every fucking times out.
Yeah.
You have to time warp it.
Yep. Okay, I see. So, so RI gives you a similar but sort of different approach to doing this, to doing that. So, you can do the recording with whatever overhead, hopefully not too high, and then you can do the replay as many times as you like, and you can do binary instrumentation in the replay. So you can run your simulator in the replay. The other thing that you can do, which we do a bit of in our debugger, which we now omniscient debugger project, is you could potentially, you can do the replays and you can shorten the lead time by doing replays of different segments of execution in parallel. Maybe it doesn't matter too much for, I guess it probably does depending on the tool. But that can be really useful if you have really intensive, if you have a big execution and you have lots of instrumentation going on. You can, and potentially you can instrument for different things. So you can have one replay that's instrumented for data cache, and another replay that's instrumented for instruction cache, things like that, which can speed things up quite a bit. So there's a lot of interesting analysis you could do this way. I guess the other thing I'm concerned about is when you do these simulations, how do you validate? Can you validate against the hardware performance counters? Because that's one thing I would really like to be able to do with RR and replay is you could actually gather the hardware information during recording, and you could compare that, and then you could do your simulation of a replay, and then you can compare the simulator results against the actual results recorded from the hardware, which would be a nice validation.
The hardware is going to be deterministic about reporting results.
I mean, it might be. What do you mean by that? I mean,
well, hardware.
The number of cache misses should be similar, right? Like,
well, okay. So it depends when you have validation, right? I mean, if the hardware is going to say this counter is counting, XYZ thingies plus or minus 20%, you're not going to get any closer than 20% on.
Yeah, I think my impression is it's usually much better than 20%. I mean, like the kinds of fuzziness that I see when we can compare actual architectural numbers for things like different kinds of instructions executed.
It's assuming that you can validate it at high fidelity. Why do you care? You're looking for bugs in your implementation or bugs in the hardware implementation?
I mean, I'm thinking of a situation where someone's written a cache simulator, and your cache simulator counts L2 cache misses, right? And your hardware also counts L2 cache misses. The numbers should agree. As
long as the simulator is simulating the hardware's cache.
Right, exactly. That's the thing. I don't actually work on these things, but it kind of since people who write these simulators tend to have, if you're not at Intel or whoever, you don't have much visibility into what the hardware really does. So you
and also inside Intel, they don't use the simulator people use in the academic world, and that's another one issue. Is totally a lot of research issues. People, especially in computer architecture, people use simulator. They are not validated, right? The number you get a lot of times are wrong. But for Intel, what I think that I don't know for sure, but they told me that what they do is they do the similar thing as Cliff mentioned. They have a huge FPGA based tracing system where you run your normal CPU. And they trace all of the state and the time and stamp them. So they trace, they stamp, and they have a huge supercomputer, and to store this because those traces are huge, and then you replay those.
Well, we would just run until we ran out of main memory. So your trace was limited by the compression of your instructions into main memory. So
how much?
Well, early machines didn't have a huge amount of RAM, but we got multi-billion instruction traces pretty readily,
Okay.
but not trillion instruction traces because
Okay.
we were going to run out of RAM. But I think in the later box, we could have done that. We didn't care by then, but I think we could have done it by then. The instruction traces compress very nicely, and you have a lot of cores, so they basically compress in the background and stream the compressed data out to main memory.
Oh, another Rob, another one is the PT, the new Intel PT one has a cycle mode now. So you have the Intel PC, as Cliff mentioned, the instructions you can compress them because like you can only remember taken, not taken, or something like that. Right?
Yep,
you can keep going, and then you can 1 bit for taken and not taken, and you can the whole block you can keep going. So the Intel PT compresses information, and then they also insert a stamp, the TSA stamps between those the compressed blocks. Like you can get quite accurate timing information for your code now. So maybe maybe that can help when you do the replay.
That would give finer grained timing information.
Very fine. Yeah, their cycle is like, as my memory is correct, it's like 100 every a few hundred cycles. You have a B something like that, right? And then you can correlate them later. So yeah,
cool.
And also there's another one is a PT write instruction. You can have a look. So what that one is that the PT write instruction, you can generate a user annotation to that trace.
Oh, cool.
So you can say I'm function A, I'm in the stack, and then you insert a tag to that trace. So later when you replay them, you can. Yeah, I'm playing this system and trying to figure out how to do some interesting.
That's pretty cool.
Filing.
Yeah. Cool.
Yeah, but the basic, just to echo the Cliff point, the instruction trees compress very nice, but the data is not. The data is not.
The data. Cool. All right.
All right. I'm going to put an end because it's getting on. I have things I want to go do. And let people get on with their day.
Thank you very much.
Yeah. Maybe an hour or two after all said and done, there'll be a YouTube link goes up for people who want to sit through an hour-long discussion. But yeah, it was fun.
Thanks, Cliff.
You can try to, maybe you can start more about our Asian Pacific, more friendly time zone. That would be.
Yeah, I'll have to think about it. I lost my evening to this. I'm not certain it's worth it. All right.
Have a good day. Thank you.
And I just got the notification 10 minutes after you started.
Yes, there was a bug in the sending. I think I sent the slides and all the emails got bounced.
Right.
And I resent them after I figured it out. So everyone got late notice.
So you know what to do with Now on Cache, but you don't know what to do with the MailChimp, right?
Of course, I'm not using MailChimp.
I'm just kidding.
So it's all good.
Yeah, no, just kidding.
I literally cut and paste on my email client. It's all fine.
Ah, okay.
All right, bye-bye.
Okay. Night, Cliff. Thank you.